Hi, everybody. This is Dr. Nigro with another chem calculation screencast. This screencast is going to focus on photoelectron spectroscopy, also sometimes known as PES. If you have questions about some of the other spectroscopic techniques that we have discussed, such as infrared, UV vis, mass spec, or just general spectroscopy, please go find those screencasts that focus on those topics. All right. So, what is photoelectron spectroscopy? All right. So, this is based on the photoelectric effect. All right. So, remember, the photoelectric effect was observed and found that if you have a particular metal, you could eject electrons from those atoms if you irradiated that metal with a specific wavelength of light. That ejected photon was observed as the production of electrical current. So let's say you had a plate of potassium and you shone red light on it and you did not observe the production of an electrical current. But when you shone purple light on it, you did observe the production of electrical current. That would tell you that the potassium atoms required purple light, which has higher energy, than the red light for those electrons to be ejected from those atoms. And remember, photoelectron ejection means that the electrons are fully ejected from the atom. They are not just moving to an excited state, then dropping back down to their ground state. They are fully ejected from that atom. So what PES looks at is it observes and records the kinetic energy of the electrons that are ejected. All right, so why does this matter? Why does the kinetic energy matter? Well, when an atom is irradiated with light, that light has a specific energy. All right. The kinetic energy of the electron as it leaves is going to be equal to the difference between the energy of the photon of the light that was shown upon the sample minus what's called the binding energy, which is represented by this phi. All right. And that binding energy depends on which element you have and which electron you are trying to eject. All right. So this is what is measured. All right. This is known based on what wavelength you set your light source to. And this is calculated. All right. So this is determined by the setup. All right. So again, the detector measures the kinetic energy, and that kinetic energy is what is left over after the binding energy is satisfied by the energy of that incoming photon. All right. Some of these electrons will be moving slowly because there's not a big difference between that photon and the binding energy. Others may be moving very quickly because there's a large difference between the two. All right. But regardless, that kinetic energy is the difference between those two energies, the photon and then the binding energy. All right. So if we want to look at the different electrons, all right, we have the core electrons and then we have the valence electrons. The core electrons are buried inside the atom, and the valence electrons are in the outermost principal shell. All right, as you can imagine, as you move closer and closer to that nucleus, all right, the energy required is going to increase. Whereas on the outside, the energy requirement is lower. All right, don't forget, Coulomb's law is in play here. It's very important. It's one of my favorite laws. I love it so much. All right, where the force of attraction between the electrons and the protons is proportional to the charge on each divided by the distance between the two squared. All right. So that means that as you get further and further from the nucleus, that R squared value is going to go up. So the force of attraction is going to go down. And as that happens, the energy required to move that electron is also going to drop. All right. So remember, Coulomb's law is what is dictating the energy required for these binding energies. And it's going to depend on which electrons you are trying to eject. If you're talking about electrons that are far removed from the nucleus, such as your valence electrons, you will not need as much energy. So you can use light with higher wavelengths. If you need to eject core electrons or electrons that are closer and closer to the nucleus, all right, then you're going to need more energy, which is why when it comes to the photon source, you can have a bunch of different choices. All right, you can use X-rays, which are pretty high in energy. These are going to focus on ejecting those core electrons. Or maybe you use a UV lamp, which is going to have lower energy. Maybe these look at your valence electrons. But the reality is you're going to use some sort of scanning technique where you move through wavelengths so you can sequentially remove electrons starting on the outside and working your way inside. All right. So what does that get us in terms of spectra? All right, I have aluminum's PES spectrum here. All right, and what it does is it compares the relative number of electrons, which is your intensity of the peak, to their binding energy. All right, and again, remember, all right, the kinetic energy of that electron is equal to the energy of your photon minus that binding energy. So this is the energy values that we see down below. All right. All right. Now you can see that this x-axis runs from big to small numbers. So this is your high energy and this is your low energy. This should be, sorry, which means these are closer to the nucleus and these are farther away. All right. So that peak position is proportional to the binding energy. All right. Higher energy, electrons closer to the nucleus. All right. And again, the intensity of that peak tells you the number of electrons that were there. All right. So if we look at this particular spectrum, we should be able to write the electron configuration starting from the left and moving to the right, starting from the nucleus and moving out to the valence shell. All right. So this first peak at 151 has 2 electrons in it. So there's your 1s2 electrons. This second peak at 12.1 is 2s2. And then at 7.19, we have 1, 2, 3, 4, 5, 6. So there's your 2p6 electrons. And then at 1.09, this is your 3s2. And then we have 1 electron. This is your 3p1. All right. So if you look, 1s2, 2s2, 2p6, 3s2, 3p1, that is the electron configuration of aluminum. So the PES spectrum of these elements should give you the electron configuration of that particular element. Now, there are a couple different questions that we can use these to answer, and I've got an example down here. All right, the complete PES spectrum of an unknown element is shown. Based on the spectrum, write the complete electron configuration. All right, so starting closest in, 1s2, 2s2, 2p6. All right, see how this one, this last is half of these guys? So that's going to be 3, whoops, S1. So there's our electron configuration. All right, now I don't know, it's kind of hard to look, but you can see that the binding energies for this spectra are not the same as those for aluminum. All right, and that's an important factor too, right? as you move across a row, the number of protons within the nucleus is increasing. All right, so what that means is that the force of attraction between the nucleus and the electrons is also increasing. Therefore, the binding energy of these electrons is generally increasing, which is why the 1s2 electrons for aluminum are around 151, whereas for this element, they're closer to 100. All right. So because this element has less protons than aluminum, all right, its electrons are not held quite as tightly. So the binding energies for all of them should be shifted a little bit lower than what we see for aluminum. All right, but let's go back to the question. Place an X above the peak that corresponds to the electrons that are closest to the nucleus. So that's going to be the ones, whoops, let me switch back to my pen. All right, so the electrons with the highest binding energy will be closest to the nucleus. And I strongly suggest you say per Coulomb's law, right? So that means that this peak right here, around a 100, is going to be the electrons closest to the nucleus. They have the highest binding energy. Therefore, the distance between those electrons and the nucleus is probably the smallest. All right, identify the element. So we need the element that has the electron configuration 1s2, 2s2, 2p6, 3s1. So we go look on the periodic table and find that that is sodium. Whoops, just spelled it wrong. All right, calculate the wavelength of the photon needed to remove the outermost valence electron. All right. So this is a little trickier. All right, we know that energy is equal to Planck's constant times the speed of light over the wavelength. So here's how we're going to get the wavelength. All right, but we need to get from this energy value to the wavelength. So the outermost valence electron is here. Oh, I'm going to have to really guesstimate what that is, but that's okay. I can make it happen. Let's say that's, I'm going to go with 0.8. It's a little tricky, right? Because you can see that they're not evenly spaced, right? 1,000 to 100 is the same distance as 100 to 10, 10 to. So if you were asked this type of question on the AP exam, they would give you that numerical value. But I'm going to go with zero 0.8, and this is going to be megajoules per mole. All right, so before I can do anything, I need to convert from energy per mole to energy per atom. All right, so the energy per atom is going to be equal to this zero 0.8. Now, mega is times 10 to the sixth. All right, that's going to get me just into joules. And this is per 1 mole. But I need to get to atoms. And so to go from moles to atoms, I need Avogadro's number. All right. All right, so it's going to be 0.8 to the sixth time, oh, not times, divided by 6.021 to the 23rd. This is going to be a small number. All right, I'm going to go with 2 digits here. 1.3 times 10 to the negative 18th. And this is going to be joules per atom. All right, so that's going to be per that electron out there. Okay, all right, so now I can use my energy formula. All right, but I'm going to reconfigure it for wavelength. So wavelength is going to be equal to Planck's constant times the speed of light divided by that energy. All right, so let's see, Planck's constant, 6.626 times 10 to the negative 34th, and that has a unit of joules times seconds. Speed of light, 3.0 times 10 to the 8th, and that is meters per second. All over my energy, which is 1.3 times 10 to the negative 18th joules per electron, not per atom, per electron. Okay, so let's do that. 6.626 negative 34 times 3 divided by 1.3 to the negative 19th, 18th. All right, and so I end up with 1.5 times 10 to the negative 7th in terms of wavelength. So that's in meters. All right. I could divide that by 1 to the ninth. Oh, not divide, multiply. And so this is around 153 nanometers in terms of light. All right. So again, you need to be a little careful if it asks you to do something like this, because remember, the energy that's on your PES spectrum is per moles of electrons. And if it's asking about a single electron, you got to convert from moles to electrons. And then you can use your formula that includes Planck's constant and the speed of light, both of which should be on your reference sheet. Don't forget your reference sheet. Okay. So again, you can use the PES spectrum first to identify an unknown element. And then second, to figure out wavelengths or frequencies of those different binding energies, those different light requirements for particular electrons using your understanding of energy, Planck's constant, wavelength, and frequency. All right, so PES is super helpful. We tend to focus only on single atoms. You can also use this if you look at molecules, but again, that's a little bit outside of the scope of what we do in AP Chem. So as long as you understand what PES is and what it measures, and then how to read one of the PES spectrums and utilize that information, you should be all set.